All right, so I was going to move on and just start calculating spin in the next video, but I thought instead I would introduce us to the idea of, or give us a little bit more introduction, I guess, to the idea of operators and sort of bring that together with the idea of the eigenfunctions and eigenvalues. I'll just put eigen there. Uh, And I also wanted to introduce the idea of the commutator because that's important when it comes to operators. And so an operator is something that if you've taken pretty much any level of algebra in school before, you've seen these before. Operators is an operator is sort of a fancy sounding name for something that's fairly common. So one operator you may have seen is the square root operator. So we have this thing, so you can think of an operator as kind of like a machine, and it's a machine and it has this little slot in it, and you can take some number and sort of insert it into that slot, and then it will output some other number. And so an operator is something that acts on something. So you could also see it. Maybe another way to picture it is we have our operator here, and it is acting on this 4 here, and that gives us a 2. Um, I mean, you can kind of make an operator out of a lot of things. You could make an operator that was something like this. So this is your operator, and what you're doing is if you operate on something, so we have this operator here, and we operate on, say, the number 10, then it will spit out 5 because our operator is just taking half of whatever we put into it. Um, and so these are also you probably heard of functions. So this could also be a function, something that is an operator that is not a function uh, would be something more like, say, taking the derivative of something. So we have this d dx here as an operator, and then you can take the derivative, you can apply that operator to something like y, and that will give us the change in y with respect to the change in x, or you could also do it to some other variable, because you can take this same operator and apply it to different variables, to different functions, really. So we could maybe more generally say that it's being applied to some general function here, and that will give us the change in that function with respect to the change in x. And another operator that we will be running into a lot are matrices. So, and a lot of times when matrices are being used as an operator, they put a little caret hat on it like that. And so this operator, we could then operate on some function, and as we will see later, we will often use the wave function, and this will give us some other wave function here. So we'll call that phi. And as I talked about in the video on Hermitian operators, then what we have is we can take our operator here and and operate on this wave function here, and that will give us the same wave function but multiplied by some scalar here. And this scalar is called the eigenvalue. So that is the eigenvalue of this operator here, and these two things are called the eigenfunctions of that operator, eigenfunction of this operator, uh, and so this operator quite often. Well, I'll get to that later on in the video. let's just talk about sort of the difference here between what's a function and what's an eigenfunction of this operator. And so if we sort of concretely define our operator as a matrix and say we give it the elements 4, minus 2, and 4, and then say we use this operator on some vectors. So if we have a vector, so these are our coordinates, the y coordinates and the x coordinates. That looks too much like a psi there. So y, and say we have some vector here that looks like this, and we'll say that that's 1 and 3. So we can multiply this by, we can take our 4 minus 2 and 4 and multiply it by our vector 1, 3, and then what we get is 4 times 1 plus minus 2 times 3, and we get minus 2 times 1, so that's just 4 times 1 plus minus 2 times 3, minus 2 times 1 plus 4 times 3, so that is 12. And then if we have 4, if we have our 4 and minus 6, that gives us minus 2. And if we have minus 2 plus 12, that gives us, that gives us, so yeah, that gives us 10. Sorry, just a kind of a brain fart there. And so we see that this should be equal here. This new vector after the transformation is going to have an x component that's minus 2 and a y component that's 10. And so we're now something like this, and we see that this has changed direction. And so this vector here is not an eigenvector of this operator. So this vector here is not an eigenvector because we see that it changed direction. Now, if we take our matrix and apply it to some other vector, say we have 4, minus 2, and 4, and we apply that to a vector that's 1, 1. So if we have that here, then we can say that that is pointing this direction, so that's 1 and 1. So that will be 4 times 1, so that's 4, and minus 2 times 1, so minus 2. Minus 2 times 1 is minus 2, and 4 times 1 is plus 4. And so we end up getting 2, 2 as our new vector, and this we can say is the same thing as 2 times this vector. Well, this vector and this vector are the same thing. It's just multiplied by this scalar. And so we can say that that what we have is our matrix here multiplied by our vector, which we'll call our psi there, and that's equal to 2 multiplied by our vector. And so we say that these two are eigenvectors of this operator here, and that this 2 is an eigenvalue of that operator with these eigenvectors. And what we're doing is we're just scaling this up by 2. So the new vector is just this 2 and 2. So it's just scaled up by 2. And that was the idea of a Hermitian well, the Hermitian had different properties, which I said was that a Hermitian operator is equal to its it's to the complex conjugate and transpose of the matrix there. Well, not necessarily a matrix, but we've been using matrices. But being an eigenvalue, or being an eigenfunction with an eigenvalue, means that this is not changing direction. All we are doing is scaling it. We scaled it by 2. You can also imagine that there might be an eigenvalue that's 1/2, which would mean that you're actually scaling it down. And you could imagine there could be an eigenvalue that's something like maybe -1, which would be the same length, but then pointing in the opposite direction. And so that is the idea of these eigenvectors here, is that when you operate on them, all you were doing is scaling them by some scalar value. And so something else I kind of forgot to mention in the video on eigenvalues and eigenvectors is sort of an interesting property, is that that the sum of all the eigenvalues, so the sum, we'll just put it like that, of all the eigenvalues, which is our lambda, is equal to the trace of our matrix operator. And the product of all of them, and the product is sometimes written with this giant pi, the product of all of them is equal to the determinant of our operator. And so you can see, so up here we had 2 as our eigenvalues. So we know one of the eigenvalues is 2. And we can also have one that is something like this. 1 minus 1. And I won't go through the calculations here just in the interest of time, but just you can do it yourself, and what you'll get is 6 minus 6. And so that would be the same as 6, 1 minus 1, which is our vector again. And so we have 2 and 6, and so we know that the trace of this is equal to 8, because the trace, as I said in a previous video, is just adding up these diagonals. 4 plus 4 is 8. 6 plus 2 is 8. So the trace is equal to the sum of the eigenvalues. And you can also see that 6 times 2, so the determinant of it was, as we know, is 4 times 4, which is 8, minus -2 times -2, which is another 4. 4 and then 4 plus, or 8 plus 4 is going to be 12. And so we know that 6 times 2 is also 12, so we get 12. So the trace is the same as the eigenvalues added up, and the determinant is the same as the product of all the eigenvalues for it. And so we talked about this as being, we used matrices in my video on eigenvectors and eigenvalues, and I think, if I remember correctly, I mentioned that matrices aren't the only things that can be eigenvectors and eigenvalues, but I did not go through what that would look like. And so I'll do that quickly here. So we can imagine that we have an operator, and we'll say it's dx, so this rather than a matrix. And so if we operate on something like, say, sine of kx, so we're taking the derivative of sine of kx with respect to x. And if you know your sort of simple calculus, you'll know that this is just k cosine of kx. So the sine and cosine sort of have this back and forth between them when you're doing these derivatives here. And so we can ask, so does k cosine of kx, so after we've done our operation on it, does that equal some scalar value here times what we were operating on, so sine of kx? And well, the answer is no. This is not the case. This isn't the same. This here, our function after we've operated on it, is not the same as our function multiplied by some scalar. However, if we try the second derivative, dx squared or dx2 of our sine of kx, what you will get is, so you take the first derivative, that's k cosine of kx, then you take the derivative of that, which is going to be, so you take the k out, and it becomes negative because the dx of cosine of x is equal to minus sine of x, but we also have to take that constant out. So what we get is minus k squared of sine of x. And so if we take our minus k squared of sine of kx equal to lambda, some scalar, times sine of kx, well, yeah, this is true if lambda is equal to minus k squared. And so minus k squared here is our eigenvalue, and it's the eigenvalue of this operator, the second derivative of our sine function with respect to x. And you'll notice if you've ever looked into like the Schrodinger equation, you'll notice that it uses second derivatives, and this is why that is the case, because you need these second derivatives of waves. This, you could say, is our wave function, is the equivalent of our wave function in this case. And that's often true, is that your wave functions are sines and cosines, because, well, sines and cosines are wave functions. They are functions that are a wave. And you'll also often see e to the ix type things, and that's because this is equal to, I believe it is, I might have this switched around, but it's something like sine of x plus I cosine of x. That's that Euler identity here. I might have the sine and cosine mixed around, but it's something like this. So this is still a wave function. So we'll see those things popping up as solutions for the wave function when we get into the Schrodinger equation in later videos. But the point that I'm trying to make here is that when we are getting eigenfunctions and eigenvalues, it is not necessarily the case that it is always a matrix. It can also be for operators such as second derivatives and things like that. And so another property that we can talk about with operators is what is called the commutator. The commutator. So you may have heard of the commutative property if you've taken algebra before, and that is the idea that if you are multiplying two numbers, say 3 times 2, that equals 6. If you switch these around, 2 times 3, that also equals 6. And so it doesn't matter what order you are putting those numbers in. And so the commutator is essentially just taking those numbers 3 times 2 and then subtracting it in the reverse order 2 times 3 and that equals 0. And so this relation here tells you that 3 and 2 are commutative. And in algebra, you usually find out that this can be more general if you have x times y minus y times x, that will also equal 0, because that's telling you that x times y is equal to y times x. But with these operators, you'll find that it is not always the case that they are commutative. And so the commutator you will often see written in these square brackets. And so you'll see that we take our operator here and then comma, then our another operator. So it's a different operator, and that is equal to the operator multiplied by the operator minus the b operator. So in the reverse order here, times the a operator. And we can show that it is not always the case. It is not always equal to 0. And one way we can show this is going back and using our matrices again. So if I say that maybe we have A is equal to some matrix that I'll say is I, 3, 4, 2, and we'll say that B is equal to some matrix that is minus 1, 2, I, 1. So these are just matrices I came up with beforehand and wrote down and did the calculations to see that these do not commute. And essentially what you're doing is you're doing just a matrix multiplication of it in one direction. So we'll have our I, 3, 4, 2, and we'll multiply that by minus 1, 2, I, 1. And from this what we get is we have, so matrix multiplication, what you're doing is you take the top row and you multiply. So we do I times minus minus 1 here, and then we do 3 times I plus I times minus 1, or I times 2 plus 3 times 1, and that gives us our first element in the matrix. In the interest of time, I'm not going to go through all of the calculations. I'll just say that after doing all those calculations, we end up with 2i for our first element, 3 plus 2i, and our second element, minus 4 plus 2i in our third element, and then 10 in that element. And then if we take these and do it in the other direction, minus 1, 2, I, 1, and then I, 3, 4, 2. So what we will end up getting is 12 plus I. We get 1, we get 3, and we get 2 plus 3i. And so if we take these and we take these and we subtract 1, so I'll just put the minus here and we'll say that that is same as right here. What we will end up getting is a matrix that has elements 12 plus I, 2 plus 2i, minus 7 plus 2i, and 8 plus 3i. And I think you will all agree that this is not equal to 0. And that tells us that these two matrices do not commute with each other. And so the question that at least for me always came up after finding out about this commutation relationship and when things don't commute is what does it actually mean? What is the interpretation of things not commuting? And so what the two interpretations, the two related interpretations that you can say is that that for commuting operators, then there is a common set of eigenfunctions. So if we have a commutator of A, B, and this does equal 0, then we can say that that the operator A and the operator B acting on the same function here will give us some eigenvalue multiplied by the same function. So they have the same eigenfunctions. It's not necessarily the same eigenvalue, so we can put an A there and a B there, but they have the same eigenfunctions. So these things right here, they have the same ones. And for those eigenfunctions, the physical quantities corresponding to the operators have definite values at the same time. And so this leads us into the commutation of well, we'll go with the usual oops, not t, that should be x greater than or equal to h bar over 2. And this is the Heisenberg uncertainty principle here. And we can see this sort of fall out of the commutation relationship between the momentum operator, which I will get into in more detail in later videos, and the position operator. So this is the momentum operator and the position operator. These are operators for different physical quantities. So obviously momentum and position. And what this is, so if then we have to multiply it by our eigenvector here, and that is going to be equal to the momentum operator multiplied by the position operator minus the position operator multiplied by the momentum operator multiplied or operating on our eigenvector here. And like I said, I'm going to go into in later videos the sort of what these operators are, but for now just sort of take my word for it that the momentum operator is equal to minus I h bar and then the partial derivative with respect to x, and the position operator is just equal to x. So it's the operator is just telling you sort of where that thing is, and this is in one dimension here. But yeah, the position operator is just telling you where in space that thing is. And so what we have is we have our minus I h bar partial with respect to x times x acting on our eigenvector here, and then that is minus x multiplied by minus I h bar partial with respect to x, both acting on our eigenvector here, our wave function, if you will. And then we can say that this is equal to minus I h bar x partial of no, not that, of the psi with respect to x, and then this is plus because we have a minus and a minus here, so it ends up being plus I h bar, and then we have our partial with respect to x, and that is acting on both the x and the psi here. So we will be using the product rule on that. So we have our minus I h bar x partial of our eigenvector with respect to x plus I h bar. Then we have x partial of psi with respect to x plus the partial of x with respect to x and psi. This here coming from the product rule, and I've just sort of carried this outside of it. And so we have this, and then you can probably see where this is going. This here is going to be equal to 1, and so what we have is minus I h bar partial of psi with respect to x plus I h bar this should have an x here. So I h bar x times partial of psi with respect to x plus I h bar x partial of psi with respect to x. You can see that this and this are going to cancel out, and so then what you have is left over is your plus I h bar psi. And so the commutator of our momentum operator with the position operator is equal to I h bar. So this operating on our psi here is equal to I h bar psi, which is decidedly not equal to 0. And so that tells us, going back to the interpretation here is the first interpretation, as I said, is that if operators commute, then they have a set of, then they share a set of eigenfunctions. And so what this tells us is that p and x, so the momentum and the position, do not share eigenfunctions, and it tells us that that the physical quantities that correspond to these operators don't have definite values at the same time. And so what that tells you is if we know p, if we know momentum, then we do not know x. And if we know x, if we know the position, then we do not know, with certainty anyway, the momentum. By the way, I should clarify, these momenta that I'm talking about are all in the x direction. And so it's not necessarily the case that if we have the momentum in the y direction and commute that with the position in the x direction, that so I won't get into that, but we just going back, assume that all of them I was talking about momentum in the x direction here. And so this is why that is the case, that we have the uncertainty with the momentum and the position. And there are other uncertainties. This is sort of the one that's often talked about. We can also have the uncertainty of the energy and the time operators. So there is an uncertainty between these ones as well, which will also be important in later videos when we start talking about things like virtual particles and things like that. But sort of the interpretation of this is that you cannot know. Well, I guess maybe an even better interpretation is that since we're saying that operating with this first and then this second is not the same as operating with this first and this second. And so it matters what order you do these things in is sort of what this commutator is telling you. Yeah, and so I think that is everything I wanted to talk about in this video. Sort of the takeaway message here is sort of what an operator actually is. It's just something you are doing to either a number or a function. And so you can, when you operate on these things, so if you operate on a number, you will get some other number. If you operate on a function, you can, depending on the operator, you can either get a number or you can get another function from it. And so you can imagine that, an operator like this, like the square root, is going to give you a number, but an operator like the derivative is going to give you another function. So the derivative with respect to x of x squared is 2x. So this is some other function here. You're getting another function out of by operating on this function here. And so we talked about how for something to be an eigenfunction of this operator, then by operating on it, you have to get the same function back. So if it's not the same function, then this is not an eigenvector of that operator. But you can take that same operator and operate on some other vector, and you can get the same vector multiplied by some scalar. And so you can have vectors that are not eigenvectors of that operator, but with the same operator you can have vectors that are eigenvectors. So it's not that if you have some operator and you operate it on a vector and you find out that that is not an eigenvector. It is not the case that you say, well, I guess this operator doesn't have any eigenvectors for it. No, that's not the case. The case is that you can operate it on some other vector, and that will give you the and that one could be an eigenvector of your operator. And that makes sense too, because if we imagine that we have our coordinates here and we have our vector here, so you can imagine that some other vector that's just a little bit off from it, when you act on this sort of entire field here with your matrix, what you will get is, say, this vector here, which maybe we'll call that A, just gets scaled up, where this one is getting scaled, but it's also because it's off of this line here, which all of your eigenvectors will lie upon. Since this one is off from it a little, it is being scaled, but it is also sort of rotated slightly in that direction. And so you can have vectors that are eigenvectors and vectors that are not eigenvectors of that same operator. And one other interesting thing we talked about is that that the trace of our operator here is going to be equal to the sum of our eigenvalues, and the determinant of our operator is going to be equal to the product of our eigenvalues. And I quick talked about sort of how you can have these eigenfunctions for an operator that is not necessarily a matrix. So you can have different operators that have eigenfunctions. And then we kind of went over this commutator relationship and showing that when you're using matrices and various operators, so for instance, this operator here, which is the momentum operator that we'll get into more in future videos, then using these operators, it is not the case that that they are always commutative. All right, yeah, I think, and we went over showing how commutating the momentum and position operators is brings us to our Heisenberg uncertainty principle here. So yeah, I think that is everything I wanted to talk about in this video, and I will see you in another video.